I am Nicole Willett, and welcome back to the fifth annual Mission to Mars Design Engineering Competition. I am the Director of Education for the Mars Society, and welcome to day two of presentations. We have a lot of really wonderful speakers scheduled. Now, just to let you know, sometimes there are some scheduling conflicts, and we don't have a lot of control over that. So hopefully, we will have everyone here today that is scheduled to be here. And today's schedule looks like we have, let's go to that, Dr. Larry Kuznetz, Dr. Gareth Morgan, and Dr. Robert Zubrin. So that is what the schedule looks like today. And then on Friday, tomorrow, you will continue planning with your team and on your own. And then Friday, we have Dr. Annika Mellis, Dr. Chris McKay from NASA, and Frank White. So that is the upcoming schedule for the rest of this week. I do want to go over some logistics here. Um, I am still working on teams. And if you have a problem or issue with your team, please email me privately. Do not put it in the public chat. If you have not heard from your team members, please email me. There have been some back and forth with different teams and team members trying to make sure that I get the time zones correct and the countries correct and placing the proper students together. So if there are any issues, email me privately and I will take care of that off the Zoom here. Make sure that you go back and watch the previous year's presentations because not every scientist and space professional presents every year. And if you go to the Mars Society's YouTube channel, you can see all the previous years. There's a playlist for the design engineering competition, and you can see all of the previous years there. And please, those are very helpful. And don't forget, artificial intelligence is not allowed in any capacity for this competition. If you or your team members use artificial intelligence, you will be disqualified as a team from the competition. It is up to you all to, as a team, to work together to make sure no one is using artificial intelligence. If you suspect a team member is using artificial intelligence, talk to them first. Have them rectify this before you turn in your papers. And if they will not rectify it, please contact me via email. And the speakers mostly have time for Q&A after their presentation. So put all of your questions for our speakers in the chat and they will be answered at the end. And our first speaker is here. Hello, Larry, how are you? Oh, you can unmute yourself?
Yeah, hi, can you hear me?
Yes, perfectly. I'm going to read your bio and then I'm going to pin you for the recording.
Let me ask you,
Yes.
can I do a screen share?
Yes. Let me give you
Mhm.
permission. That may take a moment for me to.
All
Okay.
right.
You should, in a moment, be able to share. Let me know if that works.
Um,
And I will read your bio. Dr. Larry Kuznetz is a space exploration pioneer with more than 40 years of experience helping shape humanity's journey into space. His career began during the Apollo era as a flight controller, and he later contributed to the Space Shuttle program and served as a life science experiment manager for the International Space Station. Dr. Kuznetz earned a, excuse me, Dr. Kuznetz earned advanced degrees from Columbia University and UC Berkeley, holds 8 U.S. patents, and has taught at the university level. He is also a pilot, author of several space-themed books, and has appeared on The Tonight Show. Join Dr. Kuznetz today for Beyond Artemis 2, where he will share his experiences from the history of spaceflight and discuss exciting future human exploration beyond the moon. Welcome in.
Thank you. So let me see. Share screen. Let's go to, I think it's this one. Okay. Now, can you all see?
Yep.
Okay. So we get to the beginning. Okay, everybody see that?
Yes.
Right? Okay.
Perfect. You have the floor. You have the con, Dr. Kuznetz.
I'm the calm, right? It's Kuznetz, by the way.
Oh, sorry.
It's I go by Lawrence these days, Nicole. Just in the rare possibility anybody comes up to me and meets me, that's my preference. But in any case, title of this talk is Beyond Artemis 2, How High the Moon, but Why Not Mars? First of all, I want to say that everything I'm going to tell you is from a primary source. So a primary source means that the information that's being conveyed was not told to me by somebody else. It's an important in today's world of hacking that I'm sure you're all familiar with. It's important to find a primary source because everything around you is secondary, tertiary, quaternary sources, right? So that means that I'll be talking about missions. I was at mission control for Apollo 11. I'll be talking about building spacecraft. I helped build a space shuttle. I'll be talking about life sciences. And like, as Nicole said, I was life science manager. I'll be talking about research on Mars. I've done research on Mars. I've done experiments to show that water could remain stable on Mars and of building spacesuits, et cetera, et cetera, et cetera. So I'm not doing this to toot my own horn. I'm just doing this to tell you that everything that you're hearing is from a primary source. And remember that term. Okay. So let's start out with Earthrise, and it's important. I assume we're an international group. There are no borders from space. You look at planet Earth from the moon, and this is what you see. You don't see any borders whatsoever. You see one lovely blue marble, as it's been called. This picture was taken by the crew of Apollo 8 in Christmas 1968. Where have we been in terms of leaving Earth orbit? And here are the two places that are really there's three places, but two important places subject to this talk. In Apollo in 1969, we landed on the moon in Tranquility Base, and in last month, Artemis 2, 2026, we circled the moon. At an altitude of about 4,000 miles, I should add. So let's delve a little bit deeper into this comparison because it's important to compare these. If you want to know where you're going, you must know where you've been, right? So where we're going is Shackleton Crater in the lunar South Pole. That is the target of the Artemis program. Why? You'll see why momentarily. And you can see to leave Earth, the South Pole. Can you everybody see my cursor?
Yes.
Nicole?
Yes.
Yeah, okay.
Yes. Yes.
So this is where we're going. This is what it looks like from orbit, the lunar South Pole. And around here, these craters are our target for reasons that will become pretty clear. And the goal is to build a self-sustainable lunar base. And here's some renderings of what this lunar base will look like. I assume most of you have seen this or you're familiar with this in one way or another. I want to go and compare program comparisons. So program comparisons, in Apollo, we did a design reference mission was a lunar trajectory from planet Earth. We left, we went into lunar orbit, we rendezvoused, and command module separation of lunar module landed, and rendezvous was called lunar orbit rendezvous. This is what the mission architecture looked like. If you go to Artemis, and now Artemis 4, but Artemis first lunar mission, Artemis 3 is going to be a test orbit of the landers. So we're not going to be going to the moon for Artemis 3 now. These numbers change all the time. So Artemis 4 is, well, but the point of it is to get from the Earth to the moon for the Artemis program, you don't have to be a rocket scientist to see that this is a lot more complicated architecture. There's a lot more going on here. And that's because we're rendezvousing with something, it was called a gateway, that will be sent in advance. And it's going to be a distance away from the moon. And in order to get there and to get into this orbit, this is the orbit that we're going to be in around the moon. Now, this orbit causes problems, which you will see in a moment. The destination for both of these, as I mentioned, for Artemis is the lunar South Pole. And for Apollo, it was all these sites on the near side. And it was not just one site, it was 6 sites. And that's important to remember. If anybody ever says to you, hey, we faked it, we really didn't go to the moon, then you could say to them, well, why did we fake it 6 times? Seems kind of crazy to do that. So here you see all the landing sites, right? The topography during Apollo was benign with plains and ridges. The topography during Artemis is going to be craters. And just looking at this topography, you can see this is a hazardous, rather hazardous by comparison place to go. So now I'm going to give you some other comparisons. The time to get there for Apollo was 3 days. The time to get there for Artemis, depending on this gateway or other complex orbit around the moon, could be 3 to 5 days before you actually land on the moon. Crew size for Apollo was 3 in the lunar module. It can be up to 6 for Artemis because we have Orion, which can hold more people, right? This is very interesting. This is a crux of the difference between these two programs. The landed mass for each Apollo mission was 10,873 pounds. The landed mass for Artemis is 120,000 pounds. And that's because you're landing all the pieces of a lunar base that you're going to build for sustainability in multiple missions, right? This one is very, very telling. To get to the moon from planet Earth during Apollo did not require a refuel. It was Earth to the moon in one shot. To do it for Artemis, it's going to take 17 refuels in space, and we have not done any of this yet. Radiation exposure was low because you're only on the moon 3 days. Radiation exposure on Artemis will be low if you're there a short time, to high if you're there for months. It's dangerous. This is another very telling fact. If you wanted to leave to get home from the Apollo program, all you had to do was get into the lunar module and light the engines. If you want to get home from Artemis, it's going to take you 6 days to do it. And that's because you're sitting on the moon, but the craft that is going to take you home is orbiting in this complex near rectilinear halo orbit. And you can't just get there. You have to line everything up before it's close enough for you to get there. Okay, so now let's go to the goal. The goal in Apollo is lunar history, and the goal in Artemis is self-sustainability, permanent sustainability of humans on the moon, not just going for a couple of days. And this involves extracting ice, an element called helium-3, and other resources, a lot more complex than extracting rocks. Apollo, there were no international partners. Artemis, there will be, we don't know who they are yet, what this is, and now we get to this beauty here, cost. The Apollo program to land one mission on the moon, $1.62 billion. It's going to cost $30 billion to set up this base. Target was July 1969. Target for a first landing, 2027. Those are just some of the differences between the program. Just to give you an idea, the scale difference is enormous, right? The official pitch of why we are returning to the moon is to build a lunar base in the South Pole, to extract national resources, to deploy in situ resource utilization technology that will make the base self-sustaining, to produce water, oxygen, rocket fuel, and other products for exploration, to conduct scientific studies, and to train for the next real giant step in human space exploration, which is Mars. Let's summarize that. But let's even summarize it in another way. Why are we going to the moon before Mars instead of going directly to Mars? It's closer. This is the official pitch. It's closer. It's safer. It's cheaper. It has ice, helium-3, and energy resources. It's a good Mars training analog, and the technology will evolve for Mars. I want to talk about each of these things. Because one thing, as a primary source, and you're young and you're experiencing this the first time, it's extremely important that you do fact checking. I cannot emphasize enough when somebody says something to you these days, you better say, is that really true? What are your facts? Where was your primary source? Where are you getting this information from? And don't depend on a single source ever. If you read something, I don't care where you read it these days, read it again and again and again before you're convinced. You must convince yourself. Do not believe a primary source. I mean, anything but a primary source. If you don't want to believe me, you think I'm BSing you, go ahead, but at least a primary source, right? So let's check these facts. Fact one, yes, the moon is closer. It's 240,000 miles away. Getting to Mars is a whole different story. It's 200 million miles away. It takes 3 days to get to the moon. It takes 8 months to get to Mars. These are reasons why we are officially going to the moon as opposed to Mars first. It's safer. In actuality, it is not safer. In actuality, spaceflight is dangerous. And I don't care what program, what country, who does it. There is a term you should know called LOCV. LOCV stands loss of crew and vehicle. And if you go back to the very first spaceflight that Yuri Gagarin made in 1957, I think it was, or 60 or 61, I don't remember. Maybe you do, Nicole. The odds of an LOCV are 1 in 270. That means you've got a 1 in 270 chance of not coming back. Seems like pretty good, actually. It's cheaper to get to the moon than it is to Mars. Well, that depends on how much it's going to cost you to make and sustain a lunar base. If you're talking about just sending 3 or 6 people to Mars, testing the soil and coming back, it's probably cheaper to do that than to actually build a sustainable lunar base. And here are the 3 biggies here I want to talk about now. It has ice and helium-3 and energy resources on the moon. It's a good training analog for Mars, and the technology for the moon will evolve for Mars. Let's look at those. Lunar ice from the bottom of permanently shaded craters. Let's go back a little bit. We're talking about permanently shaded craters here, Shackleton crater and surrounding craters. Supposed to have lunar ice because what we think is asteroids and comets hit the moon a long time ago carrying ice, and those craters never see the sun, and so whatever was there is still there. That's what we think based on some data. So, but the only proof we have for that is reflection proof and measurements of hydrogen. We've never sent a probe to verify that there's actually ice in those craters. And if there is ice, it's going to be dangerous and expensive and complicated to get it to the surface to use it. And depending on how long it takes to mine that ice into stuff that we can use, it could delay a real Mars mission by decades. What about this term, helium-3? Helium-3 is a rare, stable isotope of helium. It's used in medicine, homeland security, and as a potential fuel for fusion reactions. Well, we haven't gathered any to look to know exactly where and how much of it is sitting there on the surface. So it's speculative. It's unproven. We've never sampled this by robotic probes and brought it back. Extracting it and converting it to usable energy sources is not going to be easy. And it's something on the order of a fusion reaction. And you know how long we've been trying to get fusion. So this is not, it sounds great, but are you going to do it in the next week, month, year, decade, 50 years? How long is it going to take you to actually make this energy source, if you can even mine it, something that the human race can use? The last one. Oh, sorry, this one. The moon is a good training ground for Mars. Well, in this chart, I don't want to get into all the numbers, but this is a chart comparing the properties of the atmosphere and the soil of Mars with the moon and low Earth orbit and Antarctica. And no matter how you look at this chart, you come to the conclusion very quickly that Antarctica is much more like Mars than the moon is. It's a much better place to train and cheaper and faster. And so if you want to compare things as a training ground, you should be going to Antarctica. If your target is Mars, if your target is the moon anyway, well, you can do stuff there, but it's a stretch to say how applicable it really is to a Mars mission. The last one is another one that's given. The technology is needed on the moon to evolve for missions to Mars. So I'm going to give you my take on this. And you can see some photos here. The first photo on the left says, "You don't build a future on hope." So I did a PhD at Berkeley and a postdoc at NASA on Mars spacesuits. I taught the subject. I've been teaching it since 2012. I'm currently building and testing a Mars spacesuit prototype. And there's a lesson that I've learned. To try to evolve a spacesuit for Mars from a moon suit is a fool's errand. It's like trying to cram a round peg in a square hole. Likewise, for many other lunar technologies, it's nice sound bites, but the notion of going to the moon so that you can evolve the technologies needed for Mars, in my opinion, is just a false hope, and you don't need to do it. Okay, so where is all this going? Oh, I left this beauty out. Pathogen protection. It's not even discussed. Many of you probably have never even heard this term. But if you actually look at this picture in Apollo 12, you can see Pete Conrad, and around his spacesuit, everybody see this hazy stuff here? That's effluent. That's stuff coming off that spacesuit that is going in onto the surface of the moon. And just as likely, any stuff here could get into the spacesuit. And in fact, we did bring stuff back from their spacesuits when they returned. It was all over the place. Well, just imagine if there was a pathogen harmful to us that we brought back. It's a nightmare scenario, right? Well, if that's a possibility, why aren't we protecting against it in the design of lunar spacesuits? And we're not. And one of the reasons we're not protecting about it is because during the Apollo program, we quarantined astronauts when they came back from the moon for 2 weeks at a time on 3 separate missions, and we were unable to find any pathogens, and so we declared the moon pathogen-free. However, we were not going to the South Pole to ice that came from somewhere else that's never been sampled that could contain anything from anywhere. We've never done that. Would you really want to take that chance? Would you really want to build a spacesuit that doesn't take account for pathogen transfer? Okay. The scientific reality is this. If you look at the soil, the air, the atmosphere, the weather, the resources, the geology, the water history, the civilization potential, and the upside, Mars changes the equation of the Artemis program. Mars changes the equation. All right, so I've given you this whole scenario. Uh, Knowing all that, why don't we go to Mars right away? Why are we wasting all this time and money on the moon? Why don't we go there right away? Now, here are some reasons why we should go right away is the following. Mars is a backup planet. If we really ruin planet Earth and continue doing it the way we're doing it, we may need a backup planet for the human race to survive. The other thing is everything we need there for human survival is there. We don't have to transport it. It's all there. All you need is power. There's massive public interest. Well, that's why you guys are watching. You may or may not know that 5 times as many people who are on Earth have visited the Mars websites or are interested in Mars in one way or another. Here's another one. It's too far away for politics to get involved. You can get involved in politics if you're 240,000 miles away, believe it or not. It's hard to get there, and we need hard. It brings out the best of us, and youth is inspired by that. Now, let me show you this little video from a class that I once taught here at Berkeley.
NASA has long envisioned a colony of humans living and working on Mars. Are we ready to go? Yeah. Okay. These students are learning what it takes to travel to and live on the red planet. 25 years ago, this would have been a course in science fiction. Now, undergraduates majoring in everything from political science, astrophysics, computer science, engineering, astronomy, molecular biology have come together for this class at the University of California, Berkeley. Okay, we run down like this. Students share a passion.
Great. I think my generation should go for sure.
I've always wanted to be an astronaut since I was really little.
And I, for one, would love to see humans go to Mars.
You want to go?
Yeah, I'd like to go if they could send me.
Really? Okay. How many of you would want to go to Mars?
That kind of says it all. That's why you guys are watching. I mean, I don't have to try to sell this to you, right? Are scientific reasons to go? Believe it or not, you can talk about resources all you want on the moon, but we've already made oxygen on Mars. MOXIE experiment on the Perseverance rover has made oxygen and proven that the production of oxygen is easy and feasible. We've already done it. Ice and water, we don't have to go into a crater at the bottom of some place that you have to climb down to. Look at these surface features on Mars. You want ice, you dig a little bit of get the soil out of the way, get a little bit of permafrost, go to the edge of these massive craters filled with ice and scoop it out. Using that ice, you can make rocket fuel for the trip home. Production of methane and rocket fuel for the trip home from an ancient reaction called the Bosch-Sabatier reaction has already been demonstrated. If you can make rocket fuel for the trip home, you can cut the cost dramatically. And the spacesuit for Mars with pathogen protection has already been built and tested and is evolving, and it's already been used to build a suit over here that we could use for the next pandemic on Earth that would stop COVID or anything like it cold. And this is a mobile quarantine suit. It uses the pathogen protection technology that's in this Mars spacesuit prototype. You can get in it in less than a minute, and you can walk around in it. You're not grounded, and it's like you get in and zip it up from the back, and you don't have to worry. Anyway, that's a whole other talk. I don't have time for that. I don't want to make it simple. This is a challenge. It's a very difficult challenge, to stay the least 200 million miles in 8 months to get there is a challenge. Once you're there, it's a challenge. Gravity's different. There's nowhere to breathe. There's pathogens. There's risks. You say you can build enough fuel to get home. You have to prove it first. All these things are risks that you have to take. However, if it's true, if everything I've said is true so far, then why, again, I'm bringing this up. Why are we going to the moon? First, and why are we going to the moon? To set up a permanent lunar base. Here's where the talk is going to depart a little bit. A word of caution. We're going to change gears. And some people might not like what I'm about to tell you. But here's where it's coming from. I was on console for Apollo 11, 12, 14, 15, 16, and 17. I wasn't on console for Apollo 13 because there wasn't a landing. My job began when the astronauts stepped off on the surface of the moon and started doing experiments. My job was to detect how fast their life support was being used and how much time they had before they had to get back in to a safe haven. So I did this 6 times. And after Apollo 7 and after Apollo 17, there was an Apollo 18, an Apollo 19, and Apollo 20. I don't know how many have you been to the Kennedy Space Center or the Johnson Space Center, let's see, or the Marshall Space Flight Center in Huntsville, Alabama. I suspect quite a few you've been there, right? And if you go there, you've seen a Saturn V. You know what a Saturn V looks like. It's the largest rocket ever built that took us to the moon. Did you ever ask yourself, what are we doing with a Saturn V in those 3 places? Oh, I guess it was just a prototype. No, those weren't prototypes. Those were the Saturn V's for Apollo 18, 19, and 20. And I can tell you this, as excited as all you guys are about where we're going and the future of spaceflight, and looking forward to going to the moon and then stepping off to Mars, that's how excited we all were when we were on console as Apollo 14, 15, 16, 17 proceeded, and we were going to do 8, listen to the timeline, 18, 19, 20, and Mars. It was a very specific timeline. It was all there. The missions were planned. The vehicles were built. We were excited, really excited. Not much older than you, all of us working on these projects, right? So what happened? Why am I still sitting here at this point and it hasn't happened, Mars? And why is it that it won't happen at the earliest until 2027? And there's so much politics involved. So here's where we change gears a lot. We are in the midst of a new space race. In Apollo, some people called it flags and footprints because we stopped. We left early. We stopped at Apollo 17. We weren't supposed to, but we did. And so people said, oh, you just went and you grabbed some stuff and came back. Artemis is supposed to be for exploration. But will it turn into another Cold War? And who will drive the rocket ship? The billionaires, NASA, or the military? So it's instructive to look at who's driving the rocket ships right now. Well, you all know about SpaceX, and you know about Blue Origin, you know about private entities launching rockets. Let's call them the billionaires, right? The billionaires have approximately 35,000 employees working on reusable rockets. And let's contrast that with NASA, what I call the government. Let's divide the government into 2 parts, NASA and the military. Military launches rockets too. NASA has 18,000 employees versus 35,000 for the billionaires. The military has 3 million employees. The structure of the billionaires is what we call a vertical corporation. It's like a dictatorship. They make all their own decisions. They don't need to interact with anybody else, really. They make all their own parts, and they're to somewhat degree immune from politics and the government, to somewhat. NASA is a federal institution. The military is a federal institution. The efficiency of the billionaire programs, SpaceX, et cetera, is relatively high because of reusability, and it's low because NASA doesn't reuse rockets, neither does the military. This is one I want you to keep in mind. Percent of federal spending in the United States budget. The billionaires don't have any percentage because it's their own money. although they do get grants and stuff like that to do this. But their operating costs come from their own money. They started up from their own money. NASA is 0.5% of federal spending. That means every dollar of taxes that you pay, 1/2 a penny goes to NASA. The military, 22% out of every dollar spent on anything by the United States is involved in the military. And this comes down to a budget of $18 billion a year for NASA and $1.5 trillion for the Department of Defense and military, right? Keep those numbers in mind because they're going to come back. So how are we going to get there? How is the billionaires going to get there? And how's NASA or the military going to get there? Well, you've all seen these pictures. This is a picture of Starship. It is reusable. Its projected cost, we've never launched it into orbit. We've had 12 flights. We've gotten close. It's still a development program. It will go to the moon in the Artemis program, and it will and can go to Mars, assuming we develop it properly. $100 million per launch. It has been under development for 8 years. Its projected number of flights per year, once it's operational, is 20 plus. It can get to the moon and Mars, yes, both. And it's going to take 12 to 16 refuels in space to do either of those things. Here is the Artemis program, the Space Launch System. Is it reusable? No. It uses the same engines that were used in the space shuttle, believe it or not, that were reused multiple times. In fact, the engines on this Artemis 2 came from the space shuttle, as did the solid rocket boosters. The difference is, in the space shuttle program, they were reused. I think one of the rockets, one of the main engines on the Artemis program had been reused 5 times. We dropped them in the Atlantic Ocean. That's the end of them. Every single launch, they're gone. The cost for a single launch is $3 billion versus $100 million. This program's been on development for 15 years. Its projected flight cadence rate is 1 a year. Can it get to the moon and Mars? Yes. Does it need refueling? Yes. 17 refuels in the same order of magnitude as the private sector. Okay, that's comparing the vehicles. Why do I keep bringing the military into this? Seems a little strange to bring the Department of Defense, the military into this. And I'll tell you an inconvenient truth nobody really wants to face up to. Military and civilian salaries in the United States total $300 billion a year. Hardware contracts total another $700 billion a year. $1 trillion a year are spent by the military, the Department of Defense. Every 2 weeks, 3 million employees fill out a timesheet recording their hours on a project. With a code, that code is knowingly or unknowingly tied to the planning, execution, and administration of national defense priorities, which is a massive institutional incentive pointing away from space exploration and from basic human needs. So this is something that President Eisenhower warned the United States about in 1961 when he said, "Beware the military-industrial complex." Since that time, we've had 16 presidents and 3,000 congressmen. None of them have heeded Eisenhower's warning, and this is a consequence. This is the military spending that's accumulated, and this is the total number of deaths in wars that the United States have been involved in since 1950, 61, 53 actually, right? So rather than look at these charts, let's look at the summary of these charts. 7 wars, including one going on right now, $56 trillion. How do you even think of such a number? 4 million people killed. No borders changed. The cost of global security commitments comes at the expense of healthcare, failing infrastructure, K through 12 education, and yes, NASA and the future of space exploration. You want to know why I brought the military into this? This is the reason why. Here's another inconvenient truth. The same contractors that build the spaceships that are going to take us to the moon or Mars build war machines. Congressmen and senators have a vested interest in protecting the jobs of those contractors in their home states because they need to get reelected. This leads to red-blue state conflict in the United States. It leads to protecting U.S. interests overseas. It leads to conflicts with Russia and China. So ask yourself, are we returning to the moon actually to pave the way to Mars, or as an excuse to beat the Chinese the same way we beat the Russians and never go to Mars? It's just our excuse. Now, I'm not telling you that any of this is true. I can sneak away from my primary source person and tell you about some facts about spending and what has happened since 1961. Those are facts. But are we doing this to beat the Russians and never go to Mars? I don't know. So it's easy to complain. Easy to complain. Lots of people.
I agree. I agree. Larry, are you finished? Are you ready for questions, or do you want to keep?
No. I've got a pretty important part to finish up in.
Oh, okay. Sorry about that.
So another thing, another thing I want to give you guys, it's a lesson. Complaining. Nobody likes a complainer. Unless you have a solution. There's no point in complaining. That's what, look around you, look at the world around you. It's easy to complain about a lot of things, right? You're complaining about artificial intelligence. Let me tell you, artificial intelligence has enhanced my life in ways I cannot even imagine. Everything I do every day is involved pretty much with Claude or ChatGPT, and I cannot tell you how amazingly better my life is because of it. Are there concerns? You bet. But as far as me going to a doctor, what kind of doctor I'm going to see, treating an illness, getting my cars fixed, writing a screenplay, 15, 20 different projects, every single one of them, my life is enhanced amazingly by AI. That's my take on that, right? And I'm sure a lot of you have your own feelings. But that's a personal feeling. That's my personal experience. So let's get easy to complain. What's your solution? I'm going to show you a very simple, naive solution. When a military person, Defense Department person, goes into work and fills out a timesheet for 80 hours, this is what they do. They have each day for 2 weeks, and they have codes right here, and they put down the number of hours on those codes. 8 hours for weapons system logics, 8 hours for surveillance, 8 hours for target analysis, 8 hours, et cetera, et cetera, et cetera. It would be very easy to take those same people and change the charge codes. Instead of weapons system for surveillance, climate resilience. Instead of surveillance coordination, hospital medical infrastructure. Instead of defense supply chain, pandemic prevention. Instead of intelligent systems review, food production. You get the picture? Every one of these codes could be changed to a different code. These same people could be doing the same thing they do. They could come into the same place, in the same workspace, and put their 8 hours in a code that would help all of us, instead of doing what it has done, which is really ruining our lives with that. And it is, sorry, I'm on my bandstand right now because this has reached a point where I said that this talk was going to take a different direction. Obviously, it's taken a different direction. Now, I will say this. I'm not naive. You do need a bunch of hours to keep the ICBM silos going so that nobody's going to come after us. We've got enough nukes below ground to wipe out the Earth 10 times over. And a couple of nuclear submarines patrolling the Atlantic and Pacific. Nobody's going to come get us when we have these. And yes, we'll pay for them. But this is a different timesheet. And the same people could do it. They could easily acclimate to climate, healthcare, and survival. Question the narrative, why we've all allowed this to happen. That's because we learned to salute the flag and sing the national anthem early. We are being brainwashed and have been brainwashed for a long time. And a flag and a Pledge of Allegiance in the United States were born as celebrations of our independence from Britain, a symbol of unity. The national anthem was composed to celebrate an unlikely victory in a battle of independence we were not supposed to win. This is not the same thing as a rivalry with Russia and China on the opposing side of the aisle. There's an enemy to defeat. It is not the same thing. We're not created for that. National symbols were built around conflict and survival. What if we built them around exploration instead? What if our national anthem was America? Oh, beautiful for spacious skies, for amber waves of grain, instead of rockets' red glare. What spirit do we bring to space? I can get into this. I can get into advertisements which show military, join the Marines. It means the great. I could show you this. Thank you for your service. Thank you for your service. Are we really thanking people for their service? Are we really doing that? They don't want to be thanked, actually.
Please stop thanking me and veterans like me for our service. What you might not realize is that every time you say it, you could be unintentionally yanking us back to the moments we fight so desperately to leave behind.
This is not the world you think it is.
Please.
Here's another thing. If you're among the educated, fortunate, professional elite who don't have to worry about any of this, for every one of you, there are 700,000 homeless people. And in the United States, there are 339 million others whose lives are shaped by how we choose to spend our national resources. Okay, I'm done with that. Take a deep breath. That was hard. That's something you guys did not expect. Right? Let's get back to the mission. That's where we started. That's where we'll finish. At the end of the day, it's not about any of that stuff. It's about this. Look at the top picture. This picture was taken in 1968. This is the Earth. This picture was taken 58 years later on Artemis 2. Can you see a difference in these two images? Doesn't this one look more crystal clear? Doesn't this one look hazier? Now, there could be a lot of other reasons besides what we've done to the climate for this. It could be the cameras, it could be the angle, it could be the lighting. But you're talking about 1968 camera technology versus 2026 camera technology here, right? Think about it. And it's about standing on the shoulders of giants. If you want to return to the moon, listen to those who've gone before and what they've said.
Oh, we can't hear the volume.
Can't hear the volume? All right, I'll get to the point where I'll read what he says. The moon is a vast, lonely, forbidding type existence. An expanse of nothing. It looks like clouds or pumice stone. It's certainly not a very inviting place to live or work. That was Apollo 8. This is Neil Armstrong making a statement several decades later. The moon in 1969 was a greater challenge than Mars is today. And we accomplished getting to the moon in less than a decade. Are there risks? Of course there are risks. There's 10% increase in cancer risk if you go to Mars. Gravity's 38% of home. Loss of crew and vehicle, 1 in 270. Isolation, 3 years. Pathogens unknown. Other unknowns. But Many people, including Werner von Braun and a list of other names too long to list, including Bob Zubrin, of course, have said, we need to be going there. We need to be going there first. So at the end of the day, after everything is said and done, this is not about a mission. This is about changing to a planetary civilization. This is about planting a United Nations flag, a world flag on Mars. It's not about planting a United States flag anywhere. So what you just heard is a personal story. It's shaped by my personal heroes. I knew Neil Armstrong. I knew Buzz Aldrin. I know Jack Schmitt. Buzz Aldrin spacesuits hanging in my closet. I was part of the Apollo 11 team. I knew Crippen and Young and STS-1. So all of this has shaped everything you've heard. But it took a long time for me to wake up. And I'm sorry if this talk did not turn out to be what you probably thought it was going to be. But I can, in good conscience, countenance what's been happening and what we're doing and where we spend our money. Are we building a future or repeating the past with better rockets? I'm happy to answer questions, and you probably have got quite a few.
That was amazing. Thank you so much, Larry. We have several questions and we'll get through them as fast as we can. And I do want to reiterate, if you'd like to stop sharing your slideshow, I do want to reiterate that primary sources are very important. And I hope that you students understand that Larry is a primary source directly involved with the missions to the moon, the space shuttle, NASA, so much experience, and you all are so lucky to have had this presentation with a primary source. So when we say for the Mars Society competition, do not use artificial intelligence to write your paper. AI is not a place to research things about Mars. That's what NASA's website's for, and marspedia.org and many other primary sources. So just remember that. So the first question says mission control. Oh, and Yuri Gagarin was 1961. Mission control during Apollo was under a level of pressure most people can't imagine. As students, we experience a small version of that during competition and deadlines. When everything is on the line, was there a specific habit, mindset, or team practice that helped you stay calm, think clearly, and make good decisions under pressure?
It's a really good question. Of course, you train. Of course, the first time you go to mission control for Apollo 11 or Artemis, whatever it is, it's not the first time you've practiced. Just the astronauts practiced years for every switch, every controller. So do we all. We've all run test missions. We've built this up. We've been part of a team for such a long time. And I would say the most important thing that I took away from NASA is being part of a team, as opposed to being by yourself. It's gonna do you well in life. Now, just because you're part of a team does not mean you hate the other team, because hate is what we've been brainwashed to do. It's okay to be against your other football team. It's okay to root for the Knicks versus the Spurs, but it's not okay to beat them up. They're your buddies. They've got a different goal. Cherish your team. That's what I would say. Cherish your team and cherish the other teams. They're just like you. They're not out to get you.
Great answer. Great answer. The next question is, how can one land very big payloads on Mars when the planet's atmosphere is too thin for large parachutes to work, but too thick to rely entirely on rocket thrusters? And that's part of this competition. So that's a great question.
You want me to give you the answer? It's called a hypercone. It's called a hypercone, and it's called high velocity parachutes. We know how to do this. We just haven't done it with that kind of mass. We've landed, I think, 2,000 pounds The rovers are on the order of 2,000 pounds. We're going to have to land 25,000 pounds for a human mission. A hypercone is a inflatable heat, basically inflatable airfoil that as you get close to the surface, you inflate it, and it allows you to skip off the atmosphere. Now, it is a thin atmosphere, but let me tell you, it's not that thin. You're going to have reentry heating of 3, 4, 5,000 degrees because of that atmosphere. You can skip off of that atmosphere. You can do what's it called? I forgot. Air.
Oh, we may have gotten locked up here. Let's just wait a moment.
Parachutes.
You froze for a minute when you were about to say aero something parachutes. It was
Yeah.
frozen. So can
Oh,
you
yeah.
repeat that?
Yeah, aerobraking. You can use the atmosphere for aerobraking. It's thick enough so that you can use it to actually break your entry. The most likely profile is going to be you're going to approach Mars like all get out, and then you're going to use the atmosphere to aerobrake into orbit. You're not going to do a direct entry like we do for everything that we've ever done on this planet. Instead, you're going to hit the atmosphere, use it to brake and slow you down, swing and decrease your orbit. And then the next pass in your next orbit around Mars or your next entry around Mars is going to slow you down more. And eventually you're going to use the atmosphere to break you into an orbit. And then you're going to stay in that orbit for a while before you decide on a landing site. You already have primary landing sites in mind. So you're going to slow down and then go into an orbit and evaluate the landing conditions. And then you're going to do an entry, and your entry is going to be at a lower speed. And you're going to use a combination of a hypercone, engines, and parachutes to do a landing with this high weight. We've never done it. We've modeled it mathematically. It will be done probably. I think Elon is talking about, I think he just announced a human mission to Mars. It's going to be a flyby. So in order to do a flyby, in essence, you have to do aerobraking. In fact, any of the planetary visits that we've had, all the way out from Jupiter, Saturn, Neptune, all of those things have occurred because of aerobraking maneuvers. What we've done is we've either circled close to the Earth. It's called a gravity assist. So yes, gravity slows you down and kicks you out. So the combination of gravity and an atmosphere will enable you to aerobrake and carry this off. So remember, those are the three elements.
Okay. Would you mind answering a few more questions while we wait for our next speaker who has yet to arrive?
Yeah, sure. While we're waiting, I could tell you that all of my experiences are in 2 books that you can get on Amazon. One of them is called Confessions of a NASA Whistleblower. Just hit the press. Use my last name, Confessions of a NASA Whistleblower, and everything I've ever done at NASA is there. Wonderful color imagery, people I've met, things I've seen, all of it, a life story. And the other one is called Cassie's Guess, which is a novel about the first human mission to Mars, which is based on climate. The premise is that we've managed to screw up the atmosphere of planet Earth so bad that we send a human mission to Mars to try to find out what happened there first. Because Mars, as you well know, had water, had air, thicker atmosphere, and maybe life, and it's all gone. And there are lots of theories why that happened, but this novel delves into what actually happened and how it's happening here. And it's got a lot of other things, got really interesting characters, it's got great love stories, it's got great intrigue, and it's got a female computer called Cassie. CASI stands for Climate Analog Situation Indicator, and it takes place in a real place that is an amazing place to go to if you ever get a chance to go to Biosphere 2 in Oracle, Arizona. Don't hesitate. It's like an attempt at shrinking our biosphere into a series of domes. And it was originally done to see what size life support systems do we need for a Mars mission. But now it's university funded. It's a Mars analog, Biosphere 2, amazing place in Arizona. So yeah, you could get Cassie's guests, or you could get confessions, and you'll get a lot more detail than I'm giving you.
Wonderful. That's good to know. Another question is, you said life support does not allow you guesswork. You have to know how fast you're using the fuel. My question is, how did you, sir, manage to consume fuel at a high rate safely? And looking ahead with technological progress, how could we benefit from being able to use fuel even faster in the future?
Well, I assume when you're talking about life support and fuel, my end of that equation was the spacesuits, and you were talking real life support. We were talking about oxygen for breathing, and water for thermal control, and battery for power, and lithium hydroxide to remove carbon dioxide. Those were the four key elements of life support necessary for a spacesuit back then and today just as well. Because there were four of them, and because they were complex and they were going on concurrently, there was no gauge that said this is how much time you have left. What we had to do was actually use the rate of usage and project it ahead to see how long it would last. And it was not a simple forward projection. You can take a look at how fast you're using fuel in your car and say, well, at the rate I'm using fuel, I'll run out of fuel, and I can't make it to California from New York without stopping for gas or charging my car. So we all sorry, we all go through that. So we've got a lot of smart logic in cars today that tell you when to pull over so you don't accidentally run out of fuel. We didn't have that. We had that same logic back then. We wrote equations and we projected the basis of when we were going to run out of fuel, and we got pretty good at it. But in one instance, we actually there was only 2% of life support left in one of the Apollo missions by the time they got back into the lunar module. That's cutting it awfully close. But that's where your team comes in. I was part of something called a metabolic assessment team. Metabolic assessment team had three people. One was in control of the water usage, another one in control of oxygen usage, and another one was looking at heart rate and how fast you were producing energy so that it would not be used up. If you work too hard on a spacesuit, you use up your fuel faster. It's kind of like the automobile analogy. It's like putting your foot down on the gas. If you put your foot down on the gas, you're going to run out of fuel or electric power faster. Same thing in a spacesuit. If you work too hard, you're going to run out of life support sooner. So how do you stop that from happening? Well, a couple of ways. You're either fit, so you can work at a lower percentage of your oxygen maximum ability for a task, or you don't go over rough terrain. You pick your terrain. You don't climb hills when you could go around it and it's a lot easier. There are many ways to slow yourself down and use less energy, but you've got to know all of this stuff in advance before you tackle a problem like we've been talking about. You're not going to go out for 8 hours on the Mars surface and say, la-di-da, I'm just going to, lollygag back to my base and everything will be fine. You have to have multiple ways that your suit is making these, and that's the difference. When we did it during Apollo, we had a team of humans doing this in real time because we could. Because we could. We were only a second away in real time. you're going to be 20 minutes away, one way on Mars. You got a problem. You can't say, hey, my widget is not working. What do I do? You will not get an answer for 40 minutes back. And by that time, you could be history.
Right. That is so important. And I talked about redundancy on the missions on Monday when we met. And Larry, our speaker, is here for the second round. I appreciate you taking so much extra time answering questions and your wonderful presentation. This will be uploaded to YouTube later today. We have so many more questions, but for time's sake, we're not going to get to all of them. Would you mind if I emailed you some of the questions?
Sure, absolutely. Love to answer.
Okay, I will email them to you and then I will send them out to the students. Feel free to stay and watch as Dr. Morgan presents. I'm going to bring him on screen. Thank you so much, Larry, and everyone say thank you. And we will go to Dr. Morgan. Hello, Dr. Morgan, and welcome.
How's it going? Thanks for having me.
It's great. I'm going to read your bio real quick and then you'll be able to share your screen and get started.
Thank you.
Dr. Gareth Morgan specializes in using radar to study the geologic history of terrestrial planets. He is the deputy principal investigator for the Mini RF SAR instrument on the Lunar Reconnaissance Orbiter and the co-investigator of the Shallow Radar SHARAD team for the Mars Reconnaissance Orbiter. Previously, Gareth collected Earth-based radar data from the now decommissioned Arecibo Observatory in Puerto Rico. His research, drawing on fieldwork in terrestrial analog sites, focuses on understanding volcanic formations and periglacial activity on Earth and Mars. More recently, Gareth has been involved in identifying resources for future human missions, notably as co-principal investigator for the Mars Subsurface Water Ice Mapping Project. Welcome, Dr. Morgan. You have the con.
Oh, thanks very much. Right, let me try and share my slides here. So that was a bit of a challenge with Zoom. So, okay, and hopefully,
Looks good so far.
right, let's see. Does that still work?
Yep, perfect. Looks
Perfect.
beautiful.
Okay. Great. Thanks so much. And thanks very much for having me here. It's great to speak to you all. So yeah, today I'll be talking about mid-latitude ice resources of Mars. And I'll be talking specifically, well, focusing largely on radar, because as Nicole introduced, that's my background, and also talking about the Mars Shallow Water Ice mapping project as well that I've been involved in, and how this is helping us to identify where such resources could exist on Mars. So I'm going to give you a bit of a background onto Mars being, an icy planet and how we try to detect where ice is, because it's not an easy task. Then we'll talk specifically about the shallow radar, SHARAD, on the Mars Reconnaissance Orbiter and how that's contributed to our knowledge of ice at the sort of mid-latitudes. And then we'll talk about the SWIM project, the Subsurface Water Ice Mapping Project. Okay, to give you some background, so I'm sure you're all aware of this, but there's a beautiful picture of Mars taken by the Hubble Space Telescope back in the mid-90s, so quite a while ago. But I think it's great to see the planet as a whole. It has a very thin, tenuous atmosphere, about 1% that we have here on the Earth in terms of pressure. But that allows it to have a active cryosphere, and what I mean by that is there is ice, and the water can basically flux, and especially on Mars, particularly between solid and the gaseous phases. We don't know if there's currently liquid water. It doesn't seem to be. Maybe there is depth, but certainly there is a transfer of water in both gas and ice form. And so from looking at this, you can kind of see the edge of the atmosphere. You can see some nice icy clouds in this image, and then really focusing on the top, you can see the North Polar ice cap there. And so that is a big kilometers thick lump of ice, and we have one on each pole, and that makes it very similar to the Earth, right? We have a large ice cap in Antarctica and one in Greenland, as long as some other places as well. So we know that there's ice on Mars, and we're aware of that. But the question was, is it just restricted to these high latitudes, or is it elsewhere? And especially, I suppose you've been talking about resources. Water is very important for obviously life support. We need water if we're going to send humans there. We also need it. We can make oxygen from it. And critically important as well from sort of architectural designs towards like how we get to Mars and bring people safely back. Given that mass is such a premium when you make any missions, you can use water to generate fuel, and so you could fly to Mars, create fuel from ice, and then use that to launch back towards Earth. And so yeah, we know it's at the poles, but the poles aren't the easiest place to be. Just in the same way in the Earth, it's quite harsh being in the polar regions on Earth. On Mars, it's already a harsh environment. So you go into those high latitudes are challenging because you've got like the Earth, you either get long days or you get very long nights. You also get the coldest temperatures. And so ideally, we probably want to land at lower latitudes, be more preferential. And so that's why I wanted to find out where ice is in those regions to utilize it for fuel, for life support. And also, it's also important for science because it tells us something about the climate history of the planet as well. And it could also be utilized for life or preserve life. So that's why we want to do this. Okay, and so in addition to, on the poles, Mars has seasons, and that, as I said, it has an active cryosphere, so that moves ice about. And so this is an image taken from the late 70s by the Viking 2 lander on the Martian surface. And in Utopia Planitia, that's one region in the mid-latitudes in the north, it was able to capture this frost, which is deposited across. So you got this classic sort of desert landscape that you probably used to see when you see Mars, very red planet, boulders, sort of small ripples and those kind of like wind carved features. But on top of it was this ice. And so it showed the frosts were moving through the planet when it's in the right season. Just in the same on Earth, when we're in winter, you can start getting snow depending on your latitude. You don't have to be at the poles to see snow. And so it shows that ice is moving around. But obviously, this is very temporary. This is very thin layers of ice. So the question is, well, what about deeper down? If you get below the surface, there's a potential there for you to preserve ice, through the season. So even when you go into spring and summer, there's a ways that ice could be preserved at depth. And so we want to know where that ice is. And so what we've ended up doing is since Viking, both the US, Europe, and now a lot of other nations, including United Arab Emirates, India, China, are sending missions to Mars. And these missions, both orbital and landed missions, are able to tell us a lot about what's going on there and ways to detect ice. And specifically, there's been what's really happened since the late 90s with the arrival of Mars Global Surveyor, the NASA spacecraft, and then follow-on missions has really built up a nice picture, has let us understand the presence of ice and make us realize Mars is a very icy planet, not just at the poles, not just in these frosts, but also there's ice at depth across latitudes. And the reason we've been able to tell this is because you can't see it. Most of this ice is buried, is because we've now got high resolution images, and those images allow us to look for certain landscapes, certain features in the landscape of Mars, which is indicative of ice. High resolution topography, which tells us the shape and allows us to also look for signatures or slopes and things like that, which might indicate that ice is present. Thermal images. If you can monitor the temperature of the surface over multiple seasons, if you have a column of soil that has no ice and a column of soil with ice, the way they heat up and cool down will be different. And so we can use these thermal images to look for ice in that way. Neutron detection. You can look for neutrons that are cascading out of planets due to cosmic ray interactions. And if you have hydrogen in particular, that can dampen the signature of neutrons. And so that can tell you where at least hydrogen is, and possibly with ice. And then also radar is also very useful for this. And so this is just an example of some of the missions right now, which I'll be talking about, but there's more ongoing as well, and helps fill in this picture. So in terms of our evidence for ice beyond the poles at lower latitudes, one of the most striking is evidence for glaciation. So of course, on Earth, we have the polar caps, but if you go to like mountainous areas, they unfortunately are melting away, but we can still find places like in the Rockies, especially up in Canada, in the Alps, you still have these glacial features left. And so these are these ice deposits which are situated at high latitudes, and ice basically accumulate from snow being deposited. And if snow builds up into sufficient amounts, it forms ice, and that ice starts flowing downhill. And so ever since the 70s, since the Viking missions, we've noticed that there was these kind of interesting looking features on Mars that basically around high standing terrain, you had these sort of like aprons or sort of tongue-like features. And so for the last, 25 years, when we've been studying these features and getting these better images and topography, we can really measure the sort of slope of these features, and they seem very similar to the slopes you get on glaciers, and so indicative of like internal deformation due to this sort of slow fall of flow of material. We also see there's these features such as these lineations, and these lineations seem to integrate together to form these integrated patterns, very much in the same way that we see on glaciated terrain on the Earth. And so you see this around individual mountains. You also see this within craters. And this next image is actually pretty lovely. This is from the Mars Express, one of the European missions. And this sort of broad region, you can see that there's these kind of flat top mountains. And then around them is all this material that coalesces together. So you see these little valleys, they join up, you see these lines. And this material appears to flow downhill. And so this is giving the idea that these could be glaciers. We're not sure how much ice was in them, but it could either be 10% or on Earth. There must be something on the surface. It's not ice exposed on the surface, I should say. There's some layer on the surface, but it could be as much as 95% ice. And so that's what was being bounced around. But nevertheless, it shows that there's these huge ice deposits that are at latitudes down to about 35 degrees. So, the poles are at 90 degrees, this is down to 35. And when people have mapped them using image data, we find them to be hugely extensive. There's different names for them, but all these colors correspond to the same sort of feature. And you can see them at these mid-latitudes. This is 90 up here. Here's the equator here. So, as I said, in a sort of 30 to 50 degree range in both hemispheres, they're everywhere. So potentially large amount of ice there. And to give an example of another evidence to show that they're ice related, there's a latitudinal signature. The equator should be too warm on Mars to have ice. In fact, these mid-latitudes also should be too warm to have them, but if they have a little debris layer, that could protect them. And if you look at different sites at different latitudes, this panel over here is at 41 degrees, going down to around 30 degrees. You see up here, there's this valley. It's filled with this lineated material that looks glacial nature. And when you look at more southern deposits as you get towards the equator, you can see this material starts looking more degraded. And eventually here at low enough latitudes, you have ghosts. And what we mean by that is you can see the flat top mountain. Here you've had these lava flows that have flowed at some point, but something stopped the lava from flowing all the way towards the edge of the valley. And so it's been speculated that there used to be glaciers here, and that stopped the boundaries of the lava flow. And so what we call ghost ones. And what this suggests is that there used to be ice all the way down to these low latitudes, and that that ice has sort of disappeared over time, but we have some of the ones in mid-latitude preserved. And that's another signature that, as you expect, there's these latitudinal kind of patterns to them, and also suggests that over time, ice is forming at lower latitudes of Mars, and it's meaning there was more stable at lower latitudes, and then other periods of time, like the period we're in right now, it's not stable at these latitudes. And so you have this complicated climate history. It's just the same way on Earth. We have ice ages and retreats of ice. But it means along the way, some of this ice might get preserved, and that's something we could use for missions. There's been much more direct evidence of ice, so that was speculating based on the fact of, or building up evidence based on its mythology and topography, but also using the high resolution camera. This is the basically like a spy satellite camera in orbit of Mars. Each pixel is 25 centimeters. So, pretty small. So it could make out, quite clearly make out small houses if they were there present on the surface of Mars. But from this camera that it's able to see in color, we'll be able to find it at latitudes of 55 to 58 degrees. There's these cliffs basically made of ice. This blue, this is an exaggerated color. It's not real color, but the blue is corresponding to what you'd expect for ice in this here. So what you're seeing is this is the top of a slope, this is the bottom of the slope. And this is basically a cliff face. And this cliff face is materials falling off and exposing ice, showing that there's this widespread ice in this region. Not only that, but by the fact that we have all these cameras on Mars that are constantly monitoring the surface, occasionally we're able to detect where fresh impact happens. So just like on the Earth, where you probably see on the news things like fireballs in the sky, and this is from where people find meteorites in the ground. This is where you have a meteorite coming in and basically the atmosphere and burning up. And most of the time on Earth, our atmosphere filters these things out, but on Mars, there's a much thinner atmosphere. So as these space rocks basically debris from the asteroid belt is coming in, it basically can make it through the atmosphere and cause small craters to form on Mars. And some of these craters, and this one at 35 degrees latitude, once again, mid-latitude range, we've detected that it actually exposes ice. So basically this body came in, hit the ground, generated this crater, and basically spat out all this ice around here. And this shows that there's ice buried in the ground. So we have direct evidence. We do know it exists there. But as I said, it's buried, so it makes it tricky to find. So this is where the shallow radar comes in. So this is shallow radar is on the Mars Reconnaissance Orbiter. This is an active mission. It's coming up to its 20th anniversary in orbit around Mars. So it's been long running, but it's been a real workhorse. It's told us a lot of information. Has a wide range of really great um, instruments on board, including the high-res camera that I just showed you images of. There's also a CTX larger format sort of camera, spectrometers, climate sounders, all this good stuff. And then there's also the this is the radar antenna from the Shroud radar also as well on board. And just to give you a sense of scale of this thing, this is went back in JPL's Jet Propulsion Lab, where it was built out in Southern California. This is it being built, and this is the people working on it. So you get a real sense of scale. So it's quite a large body here of the spacecraft, and then of course it's got the solar panels and a large antenna as well. So the shallow radar, it basically contains this electronic blocks, not too exciting, but then it also has this antenna, which is 10 meters when deployed. It's basically a metal wire, which is a transmitter receiver within these plastic cylinders here. And this is when it was stowed. Then when we got to orbit, actuators opened this up and it unfolded. And this allows us to take radar data. And so the main takeaway here is it's 20 megahertz frequency, but that corresponds to a wavelength of 15 meters, which is quite long, but the longer the wavelength, the deeper you can penetrate into the subsurface. And so that allows us to look into from the sort of upper 10 meters down to kilometers in some locations to sort of look in the subsurface to look for ice that's buried that we can't see on the subsurface. Because, you don't always we're not always lucky enough to see these young, fresh craters exposing ice. There's a bit of a technical diagram, but basically this is the principle of how a radar sounder works. You basically have a spacecraft in orbit with this antenna, and you're essentially just transmitting radiation to the surface, almost like putting a flashlight on the surface. But what we're doing with sounders is we're sending a signal down to the surface, and then we're waiting for a response. And so when the signal bounces off the surface, in particular, it creates a large response. So you always get a big reflection. But then some of that signal also penetrates into the subsurface. And if there's structure there, we can get a secondary signal. And that allows us, and the time difference between those two signals and also the strength of power coming from those signals tells us stuff about the subsurface. These kind of sounders are used a lot, especially on glacial terrains on Earth. But the first time it was used for planetary science was at Apollo 17 in the 70s. This is the last Apollo mission to send humans to the moon. And basically they had an antenna similar to what we had for Shroud, and they were measuring, first a surface return and then subsurface structure within the volcanic terrain of the moon. This is an example. And so we're basically following this principle. And so give you a short animation of basically how it works. Here's the Mars Reconnaissance Orbiter in space. Here's the Shroud antenna. You can see there. And then essentially what it's going to do is show it's transmitting into the subsurface and receiving those images. Unfortunately, it's invisible. You don't get these cool light show if you were to see it, if you're actually to be in orbit on Mars, but it gives you a principle. And this is the North Polar Cap. And here what you can see is that by doing that and flying over and looking for these reflections both in the surface and the subsurface, we can make up this image, this cross-sectional image, which is essentially like an X-ray cut through the material. And so this allows us to see the subsurface. And this is an example of that. So this is the North Polar Cap of Mars. And this is essentially, as I said, like a shroud-based X-ray. And so this is the bed of the ice cap. And then you can see all this, like these little lines. These lines of individual layers, basically, of ice and dust. And we can use this to sort of map out structure within the ice cap. And look for evidence of like erosional features, new deposition, can tell us something about the climate. We can also use the information for assumptions about what it's made of. In this case, we know this is made of ice, and so we can use this to translate the speed of the waves through it to reconstruct what it really looks like by correcting it for the right speed, and it tells us a lot about it. And so, as we've been in orbit for 20 years, we've collected a lot of data. In this case, everywhere that you can see a color, that's an area that we have some data and shroud. And basically, whether these black dots are areas we don't have coverage, but we can see in a large area of the planet. And so I was showing you there the ice caps, but also in the lower mid latitudes as well, places like Dutralinus Mensae, they all have these kind of crazy Latin names or Greek names, or Eastern Hellas, or Flagramontes. These are areas where we also see ice that is non-polar ice, which is interesting. And so going back to when I was talking about those glaciers that we saw on Mars, and we knew about them by looking at their shape and the image data. And here's one such example. These glaciers here and here. There's a mountain. You can see this apron around it. What we were able to do is, as we flew over it with Sherrod, we were able to take readings. And what we found here is here's the surface return. We also able to find a signature of the base of these glacial deposits. And so what we're able to do is, if we can infer the thickness of these deposits based on by extrapolating the surrounding plains and assuming those surrounding plains move, are connected to the side of these mountains here. We're able to get an idea of the thickness, and we can do these inversions, and from that we can tell the properties of the material from the radar. And what it told us is that the properties of material match exactly what one would expect for pure ice. And so when we repeat this exercise for glaciers across Mars, we find out that they all have the signature. So like before, I was telling you, saying that we think these things are glaciers, but we weren't sure how much ice was in them. Was it just 10% ice and a lot of rock, or was it mainly ice with just a bit of rock on the surface? What we found out from the radar is it's largely ice, with just a bit of rock on the surface. So that was like, a huge indication. And those prior maps I showed you, where these glaciers are like in large areas of Mars, this accounts for a huge amount of ice that one could leverage. So if you were to land at these mid latitudes, you could use this ice, for life support and fuel and whatnot. And so, and here's an example. Again, this is all such mapping we've done. This is this one area, Dutralinus Mensae. All these areas in color of where we've had these glacial deposits, and what we're able to do is measure the thickness of these glacial deposits. So here they range from 15 meters down to a kilometer in some areas, so a kilometer of ice. So you can imagine just in this one area alone of Mars, there is just huge amounts of ice that we could leverage future missions. That's in the mid latitudes, but even going as far as the equator, there's evidence for ice from radar as well. So this is Medusa Fossae formation. It's kind of this wild, crazy looking material. It's also kilometers thick. It straddles the equator of Mars and has this kind of crazy textures, and Frab, it looks like it's actively eroding away. I'm not sure what formed this. One idea is it's big accumulations of ash. If you can see here, these are large volcanoes. In fact, Olympus Mons is the largest volcano in the solar system. So it could be big deposits of ash. But when we measure the properties of them using radar, so in this one particular area here, these lines are shroud tracks where we're able to measure the base of it. And if we're to take one such line going across here, you can see this is this material. We can see the base of it in the shroud data. We can also use MARSIS. MARSIS is very much like shroud, but it's a longer wavelength, so it sees deeper. And by comparing the responses we get from these two radars, it suggests that the upper layer could be like ash, but the majority of the material inside seems to have a signature closer to, or properties closer to ice. Remember with the glaciers, I said that we were able to infer the properties from the radar return. Well, here in this one, you get the same response as we did in the glacial deposits. And if that's the case, this is a map of these Medusa Fossae formation. It's this light gray material across here. And this is the equator here. This is estimates of how much ice could be buried within it. So potentially, if this radar signature is correct, there could be a huge amount of ice here. Now, the caveat here is it's buried below probably an ash layer that's about 300 to 600 meters thick. So you'd have to dig quite deep, but it does show there could be ice preserved at the equator of Mars. And then I'm coming to the end of the time here, but I just want to wrap up on the Mars subsurface water ice mapping project that I mentioned as well. So, as we've got a huge range of evidence for ice, and I just showed a little bit of it from radar and from image data, but there's a whole a whole host of body of work. There are hundreds of papers in the literature devoted to this. A group of us were tasked by NASA to try to put all that different evidence together to come up with these coherent sort of maps of where ice could be. And so we compiled a large team of experts in different specialities and different instrumentation techniques. What we're able to do is we're able to leverage data from 3 different Mars missions: Global Surveyor, Mars Odyssey, and the Mars Reconnaissance Orbiter, which I was talking about, including that neutron data, thermal imaging data, image data, and also the radar as well. What we're able to do is come up with a way to combine the results of all these. So what I mean by that is that all of these instruments are sensitive to the presence of ice. Now, there's no unique way to say, oh, there's no instrument that can say this is definitely ice or this is not. But all of these instruments can measure some material and properties in the subsurface and can tell you if the measurement is consistent with the presence of ice or inconsistent. And so we have this concept of ice consistency. And we take these 5 different techniques, and what we end up doing is, you can ignore all the details, but basically for each technique, we came up with a measurement of saying, quantifying how consistent or inconsistent was a given measurement with the presence of ice. And by putting everything into this concept of ice consistency, it allowed basically like this universal sort of currency we have between these different instruments, and allowed us to apply equations to them to sort of map out areas where lots of instruments are saying ice is present, or areas where all the instruments are saying, or lots of instruments are saying ice is not present. And not only that, but also all these different techniques are sensitive to different sections in the subsurface. So things like thermal data and neutron data, excuse me, is sensitive to sort of upper meter. But things like the geomorphics or camera-based information can tell us stuff up to the upper 10 meters, and then the radar data can tell us stuff 10 meters or below. And so by integrating all this data together, we not only can look for areas that seem promising for ice, we can also break up the potential depth of the ice into these different depth bands. And so here is the various single images we made, these ice consistency images. So we take the original data returned from these instruments and we make an ice consistency map. And from this, we can kind of add them together and create different depths maps. And so this is our shallow one, 0 to 1. And so blue pixels are where there's evidence of ice. And the darker the blue, the more evidence there is. And as one would expect, that there's more evidence for ice at higher latitudes, which makes sense because it's colder at high latitudes. But it does show there could be some subsurface ice at lower latitudes as well, which is consistent with evidence I was showing you before. And then when we look deeper into surface, 1 to 5 meters, you can see that presence of ice possibly is moving closer towards the equator. And then we can also look at greater than 5 meters. This is an area we don't have a huge amount of data for. But basically, you can put all this information together, and this allows us not only to have a map of where ice could be, so this could inform where we have landing site studies. If we're going to send new further missions to Mars, which we should do to look for ice, things like new radar missions or things like this, we can use this information to create reconnaissance zones or areas that we should focus on first to look for ice. And so from this, we're able to build up this bigger picture and understand where ice is. But I'll wrap up there. But really, the takeaway is that Mars is a very ice-rich planet. At the high latitudes, it's exposed in the surface. But even as you move towards the equator, there's evidence that substantial evidence that ice exists in the shallow subsurface as well. The further towards it, closer it gets to the equator, the deeper it becomes. But there is abundant use of resources. The challenge is using the data we have from orbit and from landers to piece that together to sort of make these maps of where ice is. But there's a lot of work left to do, but this is very positive from future missions to Mars, especially for wanting to land at these warmer regions, that there should be ice available for fuel and life support. And so with that, I'll wrap up and more than happy to answer any questions. So thanks very much.
Wonderful. Thank you so much for a beautiful presentation. The first question is, Dr. Morgan, before reading Mars from orbit, you've done field work at places on Earth that resemble it. What does getting your own boots on the ground here still teach you about a planet you can only study from far away? Great question.
That's a great question. Yeah. So when I was doing my PhD, I used to do work in Antarctica. And there's a region of Antarctica called the Dry Valleys, and this is because most of Antarctica is covered in ice, but there's these sections in the Transantarctic Mountains where you have some glaciers coming in, but ultimately it's not buried in, kilometers of ice. And so you can get to the surface, but there is ice in the ground. And what's special about Antarctica is that, especially at the high altitudes, you don't really get any rain. You don't get any rain at all, but what you get is you get snow, and even that snow when it's on the surface, even in the summer, most of that it just sublimates, meaning it goes straight from ice into gas. Occasionally you get a little bit of melting, but there's very little like liquid water. In that case, it makes it very similar to Mars. So it's a great laboratory there. There are differences, of course. But what is great from that is it allows you to walk around and understand, look at the landscape, see the different patterns and different textures and the morphology of it. And then, of course, by being in Antarctica, we're able to dig and dig into the ground to see what's buried beneath. And so, in large cases, we can dig and say, "Hey, actually, below here, there's this ice. This other area, there's no ice." But then you can compare what you see on the surface to the subsurface. And so that allowed us to collect a range of what we call of different landforms that are connected with the ice below it. And so we can understand, we can do measurements in Antarctica and say, oh, the reason the surface looks like that is because the ice is doing this seasonally. So one example is this thing called patterned ground or polygons, where you get these cool hexagonal type shapes in the ground. And those are caused by the seasonal contraction and expansion of ice in the ground. And so when we dig in those ones, indeed, we find shallow ice. When we then look at images of Mars, we can't really dig there unless we send a lander, which costs, an absolute fortune. But we can see similar features to what we see in Antarctica and make some inferences about, oh, there's that same pattern ground. That probably means that there's ice there. So yeah, there's huge value from being in the field. Now we have to be cautious because the Earth isn't habitable. We can breathe air and all that. You can't do the same on Mars. So there are differences, but it does give you that kind of like very detailed understanding of processes, how the ice shapes the landscape, how it interacts with the atmosphere above it, and we can apply those lessons to Mars.
Wonderful. The next question is, the way you map ice, you combine radar, heat, neutron, and other data because no single instrument gives you a clean yes or no. As students, we usually want one clear proof. What does it teach you to build confidence out of several imperfect clues instead of one perfect answer?
Yeah, great philosophical question there as well. So I mean, so basically, if you to do similar things on Earth, so obviously we have satellites around Earth with instruments to measure all sorts of things, right? Ice, but also things like biodiversity, say in a jungle or other terrain. What researchers would do is they would go to that area and they would make what they call ground truth measurements and understand exactly what's there. And then they would look at what the instruments in from orbit was telling them, and they can calibrate them based on that. On Mars, we don't have that benefit apart from a few locations. So, I showed you that image of where a fresh impact had thrown out ice. So we can look at those areas and say, that's a place where we're 100% confident that ice exists. There's been a few places outside the poles we know there's ice. And so we can use those locations and compare them to what our instruments are saying. And there's a few of them around the planet. And so fortunately from our work, we found that everywhere we predicted ice, everywhere we have these ice exposing impacts are areas where we thought there was ice. But we don't have the same amount of ground truth information that you'd want. On Earth, those little points here and there wouldn't be enough. You'd have this large scale ground truth, and we just don't have that for Mars. So at some point, it's the best we can understand there's instrumentation, and because we don't have the ground truth to guarantee what we're seeing, it's much better to throw multiple instruments at it than just one. Because one instrument, maybe it's calibrated poorly for whatever reason for ice. But if we throw more instruments, that gives us a better confidence. And unfortunately, it's a confidence game right now until we can get more instrumentation. And that's why it's important to get newer instruments and also to get more landings on Mars, robotic landings on Mars, to test the predictions from orbit, because that's all we can do right now.
Wonderful. And we have a student who would like to personally ask a question. Hattie?
Yeah, Dr. Morgan, it's an honor to meet you. I am Hadi Harfouch from the Dex Lab 1 team, and I have a question. The ice map you worked on might end up decaying where the first people actually land on Mars. So when student teams pick a landing site or a base site for a project, what do you usually get wrong about choosing it? Or real subsurface resource instead of just spot that it's a good place?
Okay, great. Oh, thanks very much for the question. It's a great question. So, yes, our maps, they're quite broad. They're global, but the pixels are quite large, around a few kilometers and wide. So it tells you regions to hone into, but it's very difficult to use those to pick one landing site, especially if you've got like a human going down and they've just got a small area. So I think the advice of these maps is it tells you good locations to look for instead of like right here at equator, probably a bit risky. But as you get into these blue areas, you've got more confidence. But then you need to do a second phase. And so once you've found a region within this, it's important then to take all the raw data you have from that location to make a better I guess assessment of whether there's ice there. So for example, you might zoom into this region here, look at the high resolution camera data and say, okay, there's some glaciers here. So what I would do is, based on what I've showed you about those glacial features, we're very confident they're ice. I'll make sure I land right next to one of those. Um, so my point is basically that I would use these ice maps to pick out regions, and then once you picked out those regions, use all the data sets you have available to make a much more detailed map at that location. This is meant to be a guide to show you to like which parts of Mars to look for, but not to guide exactly you would land there. And when we were making these maps, the idea was to do exactly that. It was to inform students and professional researchers of which areas have are probably the most exciting from an ice point of view. And then they would then do the next step of the work, which is to do the focus analysis, just the location. Or alternatively, the other idea is to use these maps and send new missions to go there. But yeah, if you're going to choose a landing site, pick an area that's blue and then do some more detailed work as well.
Thank you so much. Great question. Dr. Morgan, I appreciate you. Would you mind unsharing your screen, please?
Of course I will, yeah.
And I'm going to bring Dr. Zubrin up in just a moment. Would you like to answer some of the questions we didn't get to in the chat?
Yeah, I'd be happy to. No problem.
Okay, wonderful. Thank you so much. Otherwise, I can email you all the questions, but if you want to answer them in the chat, that's fine too. Thank you so much. And I will bring up Dr. Zubrin as soon as I find him on the list. He's here. I just have to find him. And make sure everyone continues asking questions. And here we have Dr. Zubrin. Thank you, Dr. Morgan, so much. All
Thanks.
right, Robert. Dr. Zubrin is here, and I will get him started with his bio. Dr. Robert Zubrin, one of my mentors for many years, is the founder and president of the Mars Society, as well as a member of the organization's board of directors. He is previously the president of Pioneer Astronautics, an aerospace and R&D company in Colorado. He is formerly a staff engineer at Lockheed Martin Astronautics in Denver. He holds a master's degree in aeronautics and astronautics and a PhD in nuclear engineering from the University of Washington. He's a respected author and a renowned expert on Mars and human space travel. Dr. Zubrin has testified in recent years before several congressional committees and in 2009 spoke in front of the Augustine Commission on the future of America's human space flight program. Hello, Dr. Zubrin, and I sent you a message with some questions that the students were asking earlier. So welcome. You have co-host powers if you would like to share screen, but not necessary.
Well, thanks for inviting me. How long is my speaking slot here?
However long you want to talk, we'll listen.
Well,
Let's say no more than 45 minutes.
okay. All right, that works fine.
Okay.
Okay, hello, and want to thank Nicole for inviting me, but also I want to thank you, the students, for choosing to participate in this engineering design contest. Now, you should know that the idea of an engineering design contest is not new, but ordinarily it's only done at the university level. That is, at better universities, it is standard to have a class in which the students are charged to design something. And depending upon the kind of engineering they're doing, that could be a fighter aircraft, or it could be a nuclear power plant, or it could be a bridge or whatever, and they're given certain constraints because, if you have to build a bridge, there's cost limitations, there's this, there's that. If you have to do a fighter aircraft, well, maybe it has to fly this high, this fast, it has to carry this much weapons, it has to be able to maneuver this way and that way, and it can't cost more than X. And a lot of times these different requirements are in conflict with each other. In fact, almost all the requirements for making something better is typically in conflict with trying to keep the cost down. But you have to work out the compromises to come up with the best possible design. Now, I was once a teacher, and then I became an engineer, and I encountered the engineering design class myself when I went into graduate school. And then I said to myself, we have to bring this into the classroom of high schools, because this is the best way to teach science, where science is not about, answering questions for tests. Science and engineering is about solving problems, about being able to do things and build things. And that's what this is all about. So the problem at hand here is designing a human Mars mission. Now, there's an enormous number of different parts of the human Mars mission, and it's much too much to address in just one class. So we've decided to focus it on the most important part of the mission, which is what you do when you're there. Okay, because the reason why we're going to Mars is not to set a new altitude record for the aviation almanac. And we're not doing it in order to have a great show for television. We're doing it to explore. We're doing it to find out the answers to fundamental questions about life and the universe, in particular, the question about life. Because Mars was once a warm and wet planet, and was so at the same time that the Earth developed life. That is, the early Mars and the early Earth were not that different from each other. They were both rocky planets with water and actually atmospheres dominated by carbon dioxide. And it was on the Earth at that time that life first appeared. So the question is, did it also appear on Mars, or did it even appear first on Mars and maybe come to Earth from Mars? How can we find out the answers to this question? And if it originated separately, did it resemble Earth life? Is it still there? Can we find survivors? Because the surface of Mars is not that friendly for life right now. Doesn't have liquid water on its surface, but there is liquid water underground on Mars. We might be able to reach it by drilling. So on Earth, you mostly find life where there is liquid water, at least in tiny amounts. The alternative is you could look for fossils on the surface of Mars in places where there was once liquid water, as shown by water erosion features, and maybe find out about life there that way. That is, instead of trying to study the present, study the past. So there's a lot of different ways to explore Mars. Now, here's the thing. the problem that's being set before you is to design an effective mission for the surface. Now, that means it's got to have a good science program, and the engineering of it also has to be right, or you will fail to do the science. So it's really these two things are the two most important things. The mission has to work. That's the job of the engineers, but it's got to be designed to really pursue an effective science program. So you have both scientific and engineering design being put in front of you. And what you're being told is, here's the amount of stuff you can have. And Nicole can correct this if this is incorrect, because I'm not up on exactly the rules this year. She'll be the authority on that. So if anything I say is different than what she says about the rules, what she says is the right answer. But you're given a certain amount of mass on the surface. As I recall, it was 30 tons that you have. And, well, how do you use that 30 tons? You can have a large crew, which would include a lot of scientists, but then you need a lot more consumables, and that means less equipment. You could go for a longer stay or a shorter stay. Longer stay gives you more person days on the Martian surface, but once again, more consumables, less robots. Or you could go the other way. You could minimize the crew and have a very large amount of robots. But then also, it's like you have to define the problem. What are you looking for? Are you going to try to, for instance, go to some place where you might be able to drill to reach Martian groundwater and look for Martian life that's still around? Or are you going to go to places where the geologic record says this was a place where there was water and for a long time, and then it slowly disappeared, and the kind of place where fossils might be laid down, and you can look at geology books for the best places to look for fossils on Earth. Where are the places like that on Mars? And once you choose the place, then you say, what's the right equipment? What's the right skills? And equipment. Okay, you say, well, I want surface mobility vehicles. Do you want a big mobile lab the size of a school bus with lots of laboratory equipment in it? Or do you want maybe small all-terrain vehicles, the size of motorcycles, that you just go around and you can deal with much rougher terrain than you can with the school bus, but obviously you don't have much in the way of scientific instrumentation with you. You'd have to gather samples and bring them back to a lab in order to study them. What use will you make of flying vehicles? We've now demonstrated a small helicopter on Mars. Could we have larger ones? Ones big enough to carry serious instruments, which Ingenuity was not, or even bigger and have astronauts riding in it. But so you're free to come up with ideas for the methods of mobility, the methods of scientific analysis, but this is not science fiction. Okay, if you design a human-rated helicopter, you got to figure out how much it's going to weigh and what kind of power system it's going to need and all that. And then that figures into your mass budget against your 30 tons that you can bring to Mars. Now, if you do choose a particular science program, okay, you got to choose the right people for that. Okay, in other words, how many people are you going to bring to Mars who are paleontologists or microbiologists or geologists, and how many will be flight engineers who you need to make sure the equipment keeps working? So what should be the personal mix? And you want this expedition to maintain high morale. So, if you think about the crew, I suppose the minimum crew is one person, but that would be a pretty lonely person. Okay. If you go with 7 people or something, what should be the mix in terms of age, gender, skills? Think of the crew and who you're going to put in command of the crew. And I do believe that part of this exercise is designing the habitat that you're landing on Mars with the crew. That is, if you're landing a crew on Mars for any length of time, they need to have a habitat. And if you want to design a habitat for, say, 7 people or 4 people, you have to make it the right size. Now, and it would have to include not only the living quarters, but the kitchen and everything, place where people can sit around and talk, maybe an exercise room, maybe a science lab. It's got to have an airlock, all these different things. You have to have a power supply for the base, okay, which could be, for instance, solar energy, could be nuclear energy. You need to look into the technologies that are available or which could be credibly available by the time of this mission. I don't know exactly the year that you're being asked to do this mission, but Nicole could tell you that. But let's say it was 2033. Well, in that case, you could choose to use some technologies that we don't quite have today, but look like, sure, we can have that in 7 years from now. All right. But you can't invoke technologies that are science fiction or are, 1,000 years in the future kind of technologies. In other words, you can certainly use solar energy or nuclear energy. I would discourage you using fusion energy because it's unlikely to be available, in 7 years from now. And if they're not, but however, if the date of this mission is the year 2050, then maybe you could use fusion energy, but you wouldn't want to use antimatter. That's further out. So what you have to do, so there are superior technologies that might be available in the future, but you have to make the case that it is credible that the technologies that you are choosing will be available in the proposed date of this mission. Okay, that obviously we don't have at the moment spacesuits that are designed for the surface of Mars, but it doesn't stretch anyone's credibility to think, well, you can go design a spacesuit that could work on the surface of Mars. And that's fine. Okay, these different kinds of vehicles that I just said, well, certainly they could be powered with electric motors. That might be possible to power them with combustion motors if you carried both the fuel and an oxidizer to burn the fuel. But once again, you can't power them with things that are essentially magic. So this is the problem that you have. Now, this is going to be interesting because you have all these different conflicting requirements. You're going to have to work it out. In other words, you might want to divide into a science team and an engineering team and a human factors team, because once again, if you make the habitat more luxurious, you're going to improve the morale of the crew, and that's important, but it's going to come at the expense of equipment, robots, other things. You want to figure out how much of each you can do. If you make the habitat just, too rough, that people have to live in little closets, then you'll attack the morale of the crew. You're going to have to, however, whatever size crew you need, you're going to have to bring enough food for it, unless you can justify that you can bring a greenhouse that can grow more food than the greenhouse weighs, because that's your trade there between growing food and bringing food. And if you do grow food, then somebody's got to take care of the greenhouse. Okay, which is one advantage of just bringing it. You don't need a farmer, but you can see that there could be advantages and disadvantages either way. If you do bring food, what food? You could say, well, the most efficient food is just to bring beef jerky, but that'd be a pretty boring diet. So you want to kind of figure it out. So this is the task before you. And now we're talking about the competition. Now we do our competition, in my view, a bit better than it ordinarily is done in a university engineering design class competition. In a university engineering design class competition, They might give several classes the same problem, okay? And, for example, design a fighter aircraft that can do all these different things. And the classes, each class comes up with a design and they present it to a panel of professors. And the professors grade them, and the one with the most points wins. Okay, well, that's one way to go. But and we're going to do that part, but we're going to do something beyond that. Okay, you're going to get a chance to listen to the other team's designs, and then the next day after you do your presentation, you're going to have a chance to raise criticisms of the other team's designs. You can point out, you could say, look, this power system that they're talking about here, they say they have 50 kilowatts of power, but they've greatly underestimated the weight of those solar panels. This is not correct. It's going to weigh much more than that. Or if they come up with some advanced kind of power reactor, you could say that's not available now, and it's completely unrealistic that it will be in 2033, or other things. Or yeah, they're looking for fossils, but the place they've chosen is really not a promising place to look for fossils. So these are real criticisms. You do not engage in personal criticisms. You don't go and say, well, those people chew rags in their sleep and you shouldn't believe in them. No, that's not a valid form of criticism. That's childish stuff. Okay, and if someone does that, anyone listening to them concludes they have nothing real to say. So you make engineering criticisms and science criticisms, and then the next day you'll each have a chance to answer the criticisms. You'll say, no, they didn't understand how this is supposed to work. Okay, we do it this way and that way, and so it will in fact work. And then after all that, that's when the judges makes their score. So you have to do the engineering design, and then you have to watch the other designs and be alert to possible flaws in them and bring it to the attention of the judges. And you want to be right in your criticism. In other words, you don't want to say something won't work when in fact it'd be easy for the other team to show that it will, because that will make you look stupid. So you don't want to do that. You want to find out the real flaws in their design and bring those to the attention of the judges. And if someone brings a criticism against your design, which is invalid, you want to be able to refute them. Okay? So you got to be quick on your feet here, relatively speaking. I mean, you'll have a day to prepare your answers, but still, you won't have weeks, you'll have a day. So anyway, that's the sketch of this. And by orienting the design around what it accomplishes on Mars, you will have the right direction to come up with a better mission design than many NASA teams have. Because in my view, many teams come up with many designs that have been developed by various NASA teams have not really been very good designs, because they were more or less designed just to go to Mars and back, and they weren't thinking about what they would accomplish when they're there. And once again, that's the most important thing about the mission. So that's what I have to say, and I'll open it up to questions.
Wonderful. Dr. Zubrin, first and foremost, several students have asked, what different types of resources on the internet or books, aside from your books, which are wonderful? Robert Zubrin has a whole library of books. Amazon has all of them. What other resources on the internet are trustworthy? I have also already told them nasa.gov, ESA's website, marspedia.org. Do you have any favorite legitimate resources that you can point to students?
Okay, my favorite one is, of my books, the most important one is The Case for Mars. That's the one that's important for this subject. I've written 13 books. You don't go to need 13 books, but that book you do need to go to. Now, let me try to think. there have been books written about Mars itself. I think William Hartman has one, which is it's like a tour book of Mars. Could probably find it on Amazon. I'm trying to think of this. And obviously, there's all the different speakers that are speaking to you as your introduction to this class. There's a book entitled The Search for Life on Mars. I think it's by Elizabeth Howell, if I'm not mistaken. But here's the thing. These books were written over time, and if you want to find books that were at least written since the year 2000, because books written now, of course, The Case for Mars, the first edition was 1996, but it was updated in 2021. There's a lot of discoveries that have been made about Mars, and since then, a good book perhaps is the one by Stephen Squires, which is about roving on Mars. He was the principal investigator of the Spirit and Opportunity mission. So those are some of the resources I could recommend.
Wonderful. Yes. And I have told the students multiple times they are not allowed to use artificial intelligence for their research or to write their paper. Absolutely not. And another question is, what is more important when they're writing their paper, explaining how the technology works that they're taking to Mars, or how are they going to use the technology on Mars?
Well, both. You want to, I mean, you don't need to explain how a solar panel works, but if something is new that people might not be acquainted with, you do want to explain how it works. If you have, let's say you design your own Mars helicopter, you do want to make it clear that it is the right size to carry either the person or the robotic payload or whatever you're going to put on it. So you may have to work through a few numbers on that. But then you want to explain the important advantages that this particular technology brings to the mission, what it will allow you to do.
Wonderful. And then a student, Hattie, has a question. Go ahead.
Yeah, thank you, Dr. Zubrin. It's a great honor to meet you. I am Hadi from the Dex Lab 1 team. You made it very clear and openly that big institutions can slow innovation down. And in this competition, we're a small team with almost no budget. Where can a small team, hungry team for innovation like us, actually move faster than giant institutions and agencies, and how can we use that?
Well, you're a small team, but you're sketching in a preliminary design. How many people are on your team?
Currently, we have 5 people.
Okay, that's enough to sketch in the design. I mean, you might want to, in other words, to have particular people lead on certain areas like science, engineering, so forth. Although you 4 or 5 people is certainly small enough to come together as a group, and where the person who leads on the science says, "Look, this is my idea. We're going to go here. We're going to go to the Valles Marineris, and this is why. And if we're going to go there, we're going to want to bring this kind of equipment." And people can say, "Well, if we're going there, why don't we bring that kind of equipment?" And you can debate it and work it out. And then if you do decide you need a certain kind of equipment, then someone's got to design that kind of equipment. Right. So there it is. But I think having a small, to do a preliminary design, a team of 5 is quite good, much better than a team of 100.
I agree. Yeah, too many cooks spoil the soup. Next question, Dr. Zubrin, in your Mars Direct plan, you focused on domestic fuel production, in situ resource utilization for the return journey. But looking further ahead, what is the biggest missing link to achieving complete self-sufficiency for the colony without relying on supply chains from Earth? Is it manufacturing advanced microelectronics locally or securing massive industrial energy sources such as nuclear fusion? Great question.
Well, the thing is this, obviously, you get increasing levels of self-sufficiency by being able to make as much stuff as you need as possible locally. And the things to start with to make locally are things that are the heaviest. This includes fuel and oxygen, water, food, basic materials like steel and plastic, aluminum, and so forth. And with this kind of stuff, you can, and maybe glass, you can make greenhouses, and therefore now you can expand your acreage. The things that you're likely to make last are the things that are the lightweight and complex. In other words, it's much easier to make 200 grams of oxygen than to make an iPhone that also weighs 200 grams. Okay. So the basically on Earth, you see the things that are big, bulky, and heavy, i.e., low value per unit weight. In general, you want to try to make locally because it doesn't pay to transport them long distances. On the other hand, things that are very high value per unit weight can easily be transported long distances, and so you don't need to make them locally. All right? Just think of how the cost of the postage compares to the cost of what you're sending. Okay? Um, you know, you could mail an iPhone to someone on the other side of the world for 1% of what it costs to buy. On the other hand, if you were sending 100 pounds of coal to the other side of the world, the postage would cost much more than the coal. So that's it. So you want to start with basic products and then work your way towards things that have a greater complexity and higher value per unit weight.
Wonderful. The next question says, Dr. Zubrin, with your nuclear engineering background, you've argued that energy is the real key to settling Mars. For students picturing a first Mars base, why does the power source matter so much? And what do people underestimate about it?
Well, look, there's really no such thing as a natural resource. There's only natural materials. People transform them into resources by developing technologies. Okay. Land was not a resource till people invented farming. Oil was not a resource until people invented oil drilling and refining and things that could run on the product. Uranium wasn't a resource until we invented nuclear power. Deuterium is not a resource now, but will be a resource once we invent fusion power, so forth. Now, in general, however, if you want to transform raw materials into resources, it takes energy. For example, say steel. Okay, the early civilizations on the Earth, for the first 4,000 years, they lived in the Bronze Age, in which the metals they could use were things like copper and tin and zinc and lead and gold and silver, which all only melt at low temperatures and are actually all fairly rare. Okay, they didn't use iron because they didn't have furnaces that were hot enough to smelt it. But then around 1100 BC, I think it was the Hittites were the first ones, but they discovered how to smelt iron, and immediately we had several hundred times more metal that we could use than we could before. Now, so you need energy to do these sorts of things. Now, on Earth, well, we have fossil fuels. but there's no fossil fuels on Mars. We can make hydrocarbon fuels, but it takes energy to create them and also to create the oxygen that's needed to burn them, which is available more or less for free on Earth because it's 20% of the air. But these are the things. To do anything, energy is the ability to do work. Just to move things takes energy. You know, it was the earliest humans had to carry everything themselves. Then they domesticated animals and developed wheeled carts to help move things. Then, but but even animals, you have to feed them. That's energy. Then there were sailboats. Well, that captures the energy of the wind. But it was a big revolution in civilization once we began to have much larger sources of energy from fossil fuels. But once again, we don't have them on Mars. What we could have on Mars are either nuclear or solar energies are the what we need, and you're going to need it if you want to make steel, if you want to make oxygen.
Okay.
Yeah.
Next question, Basmala. You may unmute yourself.
Dr. Zubrin, I am grateful for this chance. I have a question. First, I am Basmala Muhammad from Lab 2. My question is, your book isn't just about how we settle Mars. It's about why we must, beyond the science and engineering. What do you believe a real frontier does for humanity back here on Earth that makes Mars worth all of this?
Well, there's three reasons to go to Mars. One is for the science, which is what this design class is going to address. Another is for the challenge and the impact on society of accepting challenge. But the third reason why we must settle Mars is for the human future. It's to have a future that expands. It's to have a future with new possibilities. I mean, first of all, Mars, human societies on Mars will add to that future because they will, without question, add to the inventiveness of humanity. They will be groups of technically skilled people in a challenging environment, which will force them to innovate. And the inventions they come up with to help enable the settlement of Mars will also benefit people on Earth. But also, you see, there's another factor here. Okay, because what is the main threat facing humanity today? And I believe that threat is that we'll kill each other. The threat is bad ideas. The threat is, well, what was it that caused all the worst catastrophes of the 20th century? It was the idea, which came in a variety of forms, is that there isn't enough for everyone. And if you believe that there isn't enough for everyone, then everyone else is basically your enemy. Okay? That's how that goes. So, in 1912, a intellectual who was a member of the German General Staff named Friedrich von Bernhardi wrote a book called Germany and the Next War, in which he said, look, here's Eurasia. It's either us Germans or the Russians are going to get it. We're the only ones strong enough to get it. It's either us or them. We're going to have to fight them sooner or later. Should it be sooner or should it be later? He says, well, it should be sooner because right now they haven't industrialized yet, so we can take them if we take them down now. We shouldn't wait. And frankly, if you have a situation like this where you believe you're going to have to fight someone sooner or later, it's always going to be to the advantage of one side or the other to have it happen sooner, right? If it's not you, it's them. And this is the thing. Now, it is actually untrue that there isn't enough for everyone. It's actually untrue that the more people and the more nations there are, the less there is going to be for you. Because the more people, the more nations, the more inventors there are. And it's inventions that create resources. And this is why, the population of the world right now is 4 times what it was when I was born. It was 2 billion then. It's 8 billion now. And when I was young and people saw, well, the population's growing, pretty soon everyone will be starving. Okay, exactly the opposite happened. Exactly the opposite. People today, on average, are much richer than they were in the 1960s. Much richer. Okay, and especially in these countries that people talked about then as where everyone would starve, China and India, for example. They're much better off than they were then. Why? Because the more people, the more inventors, the more inventions, the more resources. And so the I mean, look at this. We're having this conversation right now over a television, telephone here. Where and I don't know where you're living right now, but it's certainly not Colorado. And here I am.
I'm living in Egypt.
Yeah, you're in Egypt. Okay, we can just talk like this. This was science fiction when I was a boy. It's reality now. Okay, so here's the thing. So this idea needs to be refuted. Now, if I tell people, well, the world's not getting more crowded, even though there's more people. There's actually more to go around than there used to be. People say, well, that doesn't make any sense. That can't be. It just doesn't make any sense. Okay. It's lying to convince someone who doesn't know geometry that there can be an infinite number of points in a 1 centimeter long line segment. That, and if you've studied geometry, that's true, that there are an infinite number of points in a 1 centimeter long line segment. It just doesn't seem believable to the average person. But if you show them a line that's going infinitely in both directions, they can believe there's an infinite number of points in that. And so the point is, by going to Mars and showing that humanity can use its creative power to expand to other planets, then we can show that it is not true that we're all enemies and we need to figure out how to kill each other. Okay. And that there's no point killing each other over provinces when by working together we can open up planets.
That is a great point. Can you repeat that last sentence?
There's no point killing each other fighting over provinces when by working together we can create planets.
That's a mic drop moment. I love it. That is beautifully stated. We have a question from my son. Go ahead and unmute yourself.
Hello, I'm Mason from Dixlab team. I'm so grateful to meet you. My questions say, if a future mission confirms that Mars can only support very limited and unreliable production of water, fuel, and energy, far below what is needed for self-sustaining settlements in the case, how would you redefine the goal of Mars exploration as a step toward true independence for Earth or as a permanently dependent extension of it? And what would you adjust in your most direct vision to respond to the reality?
Okay, well, so there's exploration and then there's settlement, and these are two different things. Although exploration will lead to settlement. The first of all, finding out what's actually there on Mars, but also after, what you're doing is like a first mission to Mars. But after the first mission and the third mission and the fifth mission, people will want to build a base on Mars that can act as a base to launch much more exploration. And a base on Mars will need to do things like grow food on Mars. Because certainly if it's one thing to send 6 people to Mars to explore, it's another thing to maintain 100 people there in a base. And we certainly wouldn't want to have to be shipping the food for that from Earth. And all sorts of other technologies involved in producing not everything that you'll need on Mars, but the biggest and heaviest things, so that you can minimize what you actually need to ship on Earth. Okay, and then this will make it possible for other people to settle Mars. So that's my answer to that. Now, if you want to know about settling Mars, there's some of it is discussed in my book, The Case for Mars. I have another book called The New World on Mars, which is specially devoted to the question of settlement in particular, which you might want to look at. But once again, resources are created by people. Okay. This place where I am right now, Colorado, when the first pioneers went west, they went right through here. They didn't stop here because they went straight from the Mississippi River, which is in the middle of the United States, and they went all the way to the West Coast. Because the land in between, they thought no one could live there. They thought no one could live here in Colorado because we get 25 centimeters of rain a year, and they were used to having at least a meter of rain a year. And they say, you can't grow anything there. No point stopping there. Okay. And then what happened, actually, it's an interesting story. They found some gold in Colorado. So all of a sudden, a whole bunch of people came here looking for gold. Okay. And some found gold, some didn't. But then most of the gold that was easy to find got used up. And then you had all these people, they're here. And they said, what are we going to do? And they figured out how to farm in Colorado and how to ranch here and how to do all sorts of other things here. And so they settled it, even though to the first glance, it didn't seem like a place you could settle. But if you have people that go to Mars, okay, they will figure out how to create resources there. Okay. And that's how you create new branches of new civilization that can take on new challenges.
Wonderful. I have a question. There's been a big debate about going to the moon versus going to Mars, and Dr. Larry Kuznetz is here. He did the first presentation today. And we would all like to know Dr. Zubrin's expert opinion on moon versus Mars.
Well, Mars is where the science is, it's where the challenge is, and it's where the future is. So I think we should go to Mars. Now, that's not to say that we can't also go to the moon. I think the same kinds of technologies that allow us to go to Mars can also allow you to go to the moon. But I think that Mars is the much more important place for us to go.
Wonderful. And Hattie, excuse me, you have a question.
Yes, thank you. This question was meant for Dr. Zubrin, I'm very sorry, for Dr. Koznek, but I will redirect it because I felt it was important. During one of his lectures, he mentioned that it might have a potential impact that we find astrobiology, the astrobiological discoveries. So how do you evaluate the balance between scientific transparency and institutional security? More specifically, if life is discovered on Mars, do you foresee the immediate release of the findings, or will protocols of strict confidentiality be implemented to mitigate potential cultural or geopolitical disruptions? And should we take any consideration while designing the missions based on transparency or secrecy?
Well, I think if life is discovered on Mars, we're going to find out about that really quick, because whoever discovers life on Mars is going to want everybody to know that they've discovered life on Mars. This is a big deal. And now it's a big deal for science, and also it's potentially a big deal for technology. It's a big deal for science because it has implications. If life is on 2 planets, it's probably on 1 billion planets. And so that tells us something about the true nature of the universe. But there's also technological implications, because biotechnology is going to be one of the main engineering fields of the 21st century. We've learned how to read the genetic code. We're learning how to write it. Biotechnology, programming microorganisms is the real nanotechnology. Microbes are the nano machines, and if we can program them, we can get them to do all kinds of things. Now, these little machines, okay, their information system is what allows you to program them, and on Earth, it's all DNA and RNA. Now, is that true on Mars? Any life form needs to have a information system, But does it have to be DNA and RNA? Okay. Here in the United States, we use the Latin alphabet. Okay. And this is used by most European countries, which, of course, is the root of the United States. And it's why we use the Latin alphabet. But there are other alphabets in the world, and they serve the same function. Okay. The Cyrillic alphabet is a little different than the Latin alphabet, but not that different. Arabic alphabets are considerably different, but they actually have, in the distant past, a common root in the Phoenician alphabet. But on the other hand, the Chinese alphabet is completely different and has no common root with the Latin alphabet at all. It doesn't even work on the same set of principles, but it does do the same job. Now, the first computers were things with lots of gears and levers, and you'd crank them and they would go and spin, and they could, do addition and multiplication and stuff like this. Then there were computers that used electrical relays, click, 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 and then vacuum tubes, and then ultimately silicon. And these different kinds of computers, actually, when you introduced a new fundamental system to the computer, you got very new and expanded capabilities. Now, right now, the information system for biotechnology is what we know about on Earth, DNA, RNA. Is it necessarily the best information system? Not necessarily. It's just the one we know. We could discover new types of biological information systems on Mars, and that would have enormous implications for biotechnology, just like switching from vacuum tubes to silicon completely changed the nature of computers.
Wonderful. And last question. Oh, actually, now all the questions are coming in, of course, at the last minute, but we'll make them quick.
We'll wind up pretty soon. Yeah.
Okay. Yeah, we'll make them quick. Dr. Zubrin, you've always been a staunch believer in producing fuel on Mars. There it goes. Using Sabatier reaction. Looking at the next generation of astronauts, what emerging chemical technology do you think will spark the next revolution in securing food and structural materials locally without relying on Earth?
Well, that's a very good question, because I think that biotech can provide us with ways to produce food on Mars in a much more compact way than you can using land, which is how we do it on Earth, with big farms or even greenhouses. I think that food can be produced with chemical reactors in an amount of space less than 1% as much as what you need using a greenhouse. And this is something that's going to be very important for Martians. It's a technology that will help enable the colonization of Mars and all other places in space where you might want to colonize. And it will be of enormous value to the people of the Earth, because what are the things that the poorest people on Earth need most? And that is inexpensive food. And if we can make it much easier to produce food, it's not like, well, gee, we're going into space and so we don't care about the poor people. It's by taking on challenges like space that we come up with the inventions that actually are the most valuable thing to the poorest people. And so doing this kind of invention of producing food in biotech reactors instead of on big amounts of land is going to do a great deal to advance life on Earth, as well as enable the settlement of Mars.
Okay, next question. In the Mars Direct plan, which proposed producing oxygen, water, and rocket fuel from the Martian atmosphere, what are the latest technical developments that make this approach more effective in terms of reducing cost and complexity compared to current NASA plans?
Well, the technical basis of producing methane and oxygen on Mars using the systems I outlined in Mars Direct, they're very well understood. What actually has advanced in, say, the past 20 years our knowledge of where you can find water on Mars. And now we know we can find lots of water in lots of places because there are glaciers on Mars of pure water ice that come as far south as 38 degrees north, which is the latitude of Athens on Earth. You know, you don't have to go to the North Pole to find ice on Mars. A lot of this is covered with a meter or so of dust, so you don't see it with telescopes, but you can see it with ground penetrating radar. And that's where we could land and get all the water we need. I'm going to have to go, so I'll take one more question.
Okay, where should we focus our research efforts on advancing rocket propulsion technology or on developing life support and in situ production systems on Mars?
The latter. Okay, the rocket systems are being developed for many reasons, including by SpaceX. They're being developed because there's all sorts of commercial markets for being able to deliver stuff to orbit. What we have to do is work on the stuff that is beyond the horizon of immediate profit, which is the stuff we need to settle Mars. And the question of how you turn Martian materials into resources, that's the question of settlement. A place is habitable for you if there are resources there for you. And once again, if you're living by the side of a lake, if you know how to fish, there's food there for you. If you don't know how to fish, there's no food there for you. Okay, so the question of whether there are resources in that lake does not depend on the lake, it depends on you. Okay, so we have to figure out how to be able to make everything we need on Mars. And once we do that, Mars will have abundant resources as far as we are concerned.
That is very well said, Dr. Zubrin. Thank you from myself and all of the students in attendance. We appreciate you taking your time to speak to us. And I'm looking forward to the contest, and I will send you all the reports when they are finished, and you're welcome to join us for the competition itself.
All right. Thank you, and good luck to everyone.
Thank you. Bye.
Bye.
Okay, students, as we wrap up this final minute or two here, I just want to give you some reminders. Primary sources are essential, as Dr. Kuznetz said at the beginning. Please do not use artificial intelligence. If you have an issue with your team, if you are not getting along with a team member, if a team member is not participating, or if you have not heard from your team members, please email me today. All videos will be uploaded the day of the presentation, and we will meet Friday. So tomorrow, continue gathering with your team and start planning your responsibilities. If you don't have a team name yet, please get one and send it to me. Friday, we have 3 speakers, Dr. Annika Mellis, Dr. Chris McKay, and Frank White. So everyone, email me any issues, any problems, and thank you for your time and attention today. I am so looking forward to the rest of this competition, and I hope you all have a wonderful day. Bye, everybody.